MIMO antenna for 5G systems using complementary split ring resonators. In this paper, a MIMO antenna is proposed for 5G applications. Every antenna is mounted on the top layer of substrate in the form of rectangular patch. Each antenna is fed through transmission line, and the transmission line is connected with quarter wave transformer for impedance matching. The substrate used in our design is Rogers RT/duroid 5880, TM. Circular split ring resonators are designed on the ground plane to increase the bandwidth and the efficiency of our antenna. The antenna resonates on the frequency of 28 GHz. The gain secured by the antenna is above 8 dB with a bandwidth of 2.82 GHz. The simulation results have substantiated a good performance of the MIMO antennas, thus making them suitable for many 5G devices. Keyword CCSR, 4G, 5G, MIMO, high bandwidth. Introduction. Wireless communication plays a vital role in our daily routine life. Recently, scientists are working on 5G systems which will give us high data rates and increased bandwidth. Higher bandwidth also gives us more numbers of users as the frequency channels are increased. 5G has less interface and better efficiency than previous wireless technologies. It also has lower latency and greater capacity of remote execution. In order to achieve better bandwidth, and high gain antennas are very crucial. The amplifier also enhances overall gain of the system but complex in circuitry, so instead of using amplifier, use the antennas which give us better performance on simple optimizing techniques. Recently, many researchers have modified patch antennas to increase bandwidth. A single element microstrip patch antenna is proposed in one, feeding with a transmission line at operating frequency of 28 GHz. The inset fed point value is 0.2 mm and bandwidth of 1.29 GHz. In 2, the microstrip antenna is operated on 4 different frequencies, 3.05, 3.75, 4.55, and 4.9 GHz. 3 elliptical slots are etched to expose the feeding strip for impedance matching with maximum bandwidth of 2.33 GHz. A 2-dimensional compact slotted antenna consisting of 8 elements array was proposed for 5G applications in 3 with the bandwidth of 1.38 GHz and a gain of 9 dB. Although the gain of array antenna is high, but its bandwidth is not much higher. In 4, a compact dual-band microstrip patch antenna is proposed for 5G applications. The antenna is operating on 10 GHz and 28 GHz with a gain of 5.51 dB and 8.03 dB. The bandwidth of the antenna is 0.278 GHz and 1 GHz at frequency of 10 GHz and 28 GHz respectively. In 5, a PIFA antenna is designed for 5G with the gain of 4.5 dB. Feeding and shorting of the antenna is done using metallic strips. The bandwidth of antenna is 1.55 GHz. A dual-band circular patch array antenna is designed in 6. The antenna is operated at 28 GHz and 45 GHz with the bandwidth of 1.3 GHz and 1 GHz. Although antennas proposed in 1 to 6 proved to be good candidates of 5G systems, however, their bandwidth was limited, which results in less number of users and data rates. MIMO antennas use multiple signal paths to gain the knowledge of communication channel. By using spatial dimensions, MIMO antennas achieve significantly higher data rate than a single element and an array antenna. In this paper, we proposed the 4-element MIMO antennas with complementary split ring resonators, CSRR, having a bandwidth of 2.82 GHz. The antenna is operated at 28 GHz with the gain of 8.29 dB. The design of our MIMO antenna is discussed in Section 2, while Section 3 is about parametric analysis, results, and conclusions are in Sections 4 and V respectively. 2. Antenna design. The top view of the MIMO antennas are shown in Figure 1. There are 4 microstrips patch antennas, all are placed just little away from the edges with a distance of 0.328. The horizontal and vertical distance between the 2 antennas is 0.404 and 0.931. Respectively. Rogers RT/duroid 5880, TM, is used as a substrate having equals 2.2 and tan equals 0.0009. The thickness of the substrate is 0.073. All the antennas are composed of patch, transmission line, and quarter wave transformer. The patch is connected with the quarter wave transformer, and quarter wave transformer is further attached with the transmission line through which our antennas are fed. Quarter wave transformer is used for impedance matching between the patch and transmission line. The patch, P2, length is 0.262. And its width is 0.396. The length and width of transmission line, T2, is 0.25. And 0.033. Respectively. The dimension of quarter wave transformer, Q2, is 0.366. And 0.226. The bottom layer is composed of CSRR. The purpose to use this is to increase the bandwidth of the antenna. As you see in Figure 2, there are 2 CSRR exactly on the backside of all the 4 patches of antennas. The center point of both CSRR are same but their radius are different. The radius of CSRR1, C1, is 0.093. mm and CSRR2, C2, is 0.112. When we draft the circular rings on the ground plane, the antenna could not operate on our desired frequency because impedance is not properly matched. We resolve this problem by flattening the patch edges of all the antennas as shown in 3. Parametric Analysis. Parametric analysis is carried out on our MIMO antenna to achieve the best results and for better understanding of our design. Parametric analysis is performed on the patch width and on the edges. The parametric analysis on the width is shown in figure 4. We performed parametric analysis on width to obtain the best result of S11. As it is clear from figure 4 that when we increase width of patch, the S11 graph moves towards lower frequencies. For better impedance matching, truncation on edges of patches is performed, and its parametric analysis is shown in figure 5. As it is seen from figure 5 that when we increase truncation area, the S11 graph moves towards higher frequencies. 4 results. The S11 comparison of MIMO antenna with and without CSRR is shown in figure 6. As it is clear from the figure that the MIMO antenna operates on our desired resonating frequency. With addition of CSRR, impedance matching is increased, without affecting the operating bandwidth. It operates in the range of 26.70 GHz to 29.52 GHz, having a bandwidth of 2.82 GHz. Gain is directly proportional to the directivity of the antenna, so if the antenna has high gain then it's more directive. The gain of our MIMO antenna with CSRR is shown in figure 7, and we see the directivity of our antenna in radiation pattern, which is shown in figure 8. As we see from the figure 7 that our gain is high, which is 8.29 dB, then accordingly our antenna is more directive. We see that in figure 8 as well. The mutual coupling between each antenna is shown in figure 9. As we see from the figure that the mutual coupling between each antenna is below from -20 dB, therefore it can be claimed that these radiating elements have very less coupling between all of them. V. Conclusion. A layout of 4x4 MIMO antenna is presented for 5G communication systems. The resonating frequency of the antenna is 28 GHz. The antennas indicate a compact geometry and a better bandwidth of 2.89 GHz, ranging from 26.70 GHz, 29.52 GHz. Our antenna shows an acceptable return loss and radiation performance with a feasible gain of 8.29 dB, thus making it suitable for 5G utilization in the area of communication.